Hello, I'm audible?
Yes, sir, audible, sir.
Okay. Okay, let us start. Slide is visible, please.
Yes, sir, visible, sir.
Okay, so welcome in week at hydraulic engineering PMRF live TA session. So basically the week 8 was about the pipe flow. Here we discuss about only the pressurized flow. Pipe flow maybe, let me take black one. Here is a fully. So pipe flow may be your open free surface flow or open channel flow or pressurized flow. So here we will discuss about pressurized flow and the topic related pipe flow we discuss here the laminar versus turbulence in the pipe, how the your velocity profile in the pipe in case of when the flow is laminar, that is your RE value less than equal to 2000 or somewhere 2100, that is in laminar case, and how your velocity diagram in the turbulent case in pipe flow, what is entrance region and what is fully developed region. So we have discussed these things earlier also, but here very small, very few minutes I will discuss in very few minutes. And laminar pipe flow analysis, Newton's second law, Newton's equations, that is Navier-Stokes equations, and the dimensional analysis. So basically how you will get the equations using the Newton's second law, Navier-Stokes equation, and dimensional analysis we'll see also. I think sir has also discussed very well, and I have taken PPT from the class of hydraulic engineering, so I will not discuss here, just for solving the problem which I have taken here. Just I will show you some formulas and concepts regarding the laminar pipe flow. Now, the third things, pipe flow analysis, that is your Darcy's friction factor and energy considerations. So this is also important. And from this, from here and here, these two topic is very important as the exam point of view at undergraduate level, like GATE exam and other state engineering exam also, and your assignment also. So these two topic is very important. The question is like that sometimes, the question framed like that, the velocity in case of laminar and velocity in case of turbulent. Sometimes question like that, find out the Darcy's friction factor. Sometimes the your using the Bernoulli's equation calculate the pressure at point A. If the your question, if pipe is flowing from this direction, water is flowing point A and point B, some angle is there, let's suppose theta. So theta from horizontal. So what is the pressure at B and velocity? It may be depend on the question. And turbulent flow in pipe, it is very important. Question from this turbulent flow pipe is very less comparatively these two topics. So we'll discuss more uh, with the problems also. So I have discussed earlier also the pipe generally you will see circular in nature because of there's an advantage, lots of advantage, that is the minimize the frictional losses, prevent the uneven pressure gradient because at here maybe the uneven pressure gradient, distributed stress evenly in the circular pipe. So that's why generally we consider the pipe as a circular. Just for your information, Reynolds number is very important thing here. Your inertial force and the viscous force. Basically based on Reynolds number we divide the flow in turbulent as well as, let me put it in full view mode. Your Reynolds number is the inertia force and the viscous force, which is rho V average d by nu, and d here is the characteristics length of geometry. Here d is the characteristics length of geometry, always remember. And here we have taken the v average. You know already the difference between point velocity. I think you might be not able to see. Let me share in the full view mode, then you can easily see. Now are you able to see in the full view mode? Please tell me.
Yes, sir.
Okay. So this is the very basic things, and where how the difference, actually the relation between your point velocity and average velocity, you know already we will consider, and we have already discussed also one kinetic energy correction factor, and I have question regarding that, your kinetic energy factor in laminar and turbulent, and kinetic and your momentum correction factor, that is the energy correction factor and the momentum correction factor. We have a question related to these two terms. So moving ahead, always remember sometimes in case of pipe flow we generally tell about the your D is nothing but, I think I have, yes, here if you will see your hydraulic diameter, you can see, you can say your rho g whatever is there, your Reynolds number is rho v d, or you can say the dh by your p, that is your mu. So your dh is nothing but it is the hydraulic diameter, always remember. But when you calculate your hydraulic diameter for circular, you will get directly d. Here you can see. So this is important. Sometimes people forget about, in case of open channel flow, what is the Reynolds number. You always remember Reynolds number is this dh. It, if you will put the dh here, that is your hydraulic diameter, it will be applicable for open channel and also your pressurized flow, that is pipe flow or pressurized flow, any type of. So remember these things. And here it is given laminar flow 23, somewhere 2000, somewhere 2100. In between you will always see laminar flow Reynolds number is 2300, and transition in between 2300 to 4000 and greater than 4000 is turbulent flow. So we have already discussed these things. And here the laminar and turbulent flow how look like practically. If you will see the smoke, here some experiment, the laminar flow is behave like that. If you will see very smooth, there is no zigzag motion. But if you will see in the turbulent flow, there is a smoke in zigzag way. So here you can also see in the turbulent flow, your fluid particle is flowing like that. So here fluctuation is very high. If fluctuations is very high, lots of things will happen in the turbulent flow. We will discuss. That is very important. And if you will see in the laminar flow, there is particle is flowing in a straight direction. There is no zigzag motion kind of thing. So this is very important thing. So now the entrance reason, this is very important. Sometimes uh, question on the basis of entrance reason and what is a fully developed reason, people ask. So remember always the your hydraulic or hydrodynamic entrance reason is nothing but up to, it is basically a length. It is a length. If we are discuss here about the pipe flow, so it is length basically. Hydraulic hydrodynamic entrance reason is a length. In between the length your velocity profile is developed or change, keep on changing up to a certain length. And what is the length? If you will see here, the length formula, your LE is equal to 0.06 RE into D. So this is the length for laminar. If water is flowing laminar, then this formula, and if water is flowing, your condition is turbulent, that is formula is this. So remember, so entrance region is nothing but it is a length in which your velocity is developed. After that, velocity will not change. Your velocity profile will not change. Here, if you will see, the shape of the velocity profile is different. Here, different comparatively to previous one. Here, different. But here is from this reason, if you will draw another velocity profile, what you will see, this velocity profile and this velocity profile will look like similar. Okay. Just think this is a similar. So after that similar, and sir has also discussed in the lecture very well, so please follow the lecture also. just for your just for recapitulation, I have discussed here, because it's when again and again you will see, then definitely you will get the thing. Then here the same things in the bigger zoom view, if you will see. Now moving ahead, okay, your velocity diagram is like that. But this velocity diagram is in the laminar flow. But if you will see the turbulent flow, there is a zone. Your here first I want to show you the velocity diagram in the laminar case. If you will see, in laminar case the velocity diagram, and in turbulent case you will see the changes of the velocity diagram. Here is a perfect parabolic kind of thing, if you will see here, but not the perfect parabolic. So the reason behind it, the reason is your fluid particle is flowing in the zigzag way in case of turbulent flow, not in the smooth smoothly or in the straight direction. But in case of laminar flow, your water is flowing in the layer wise or sheet wise, so velocity is like that, velocity profile is fully parabolic. And in turbulent not. So here it is very important thing. In case of sometimes you may expect this diagram, this both diagram in the exam, maybe your gate exam or also maybe another exam. What is the difference between some pictorial representation will be given in the question, and maybe the option will be on the base of which one represent the turbulent flow and which one is the laminar flow. So always remember the diagram. So here the layer in between the, basically in the case of turbulent flow, your velocity profile having some layers, that is the viscous layer which is very near to wall, which is very near to wall, this is the your viscous sublayer, and after that little bit above it's the buffer layer, and then after overlap layer, and then after turbulent layer. So please, I will suggest you go through some standard book or maybe video also, and please try to find out the what is the meaning and what is the significance and how this things is developed in the turbulent flow. But in case of laminar flow, these things is not developed. So how it come in the picture in the turbulent flow? So one reason is that your velocity, but another reason also you please try to see. Now moving ahead some years from here, I have taken the slide just from the hydraulic engineering lecture. So you just what we have discussed earlier, your entrance region, basically your pressure is dropped in the entrance region, your, that is pressure is balanced by viscous force and the acceleration. And what is the meaning of these things, the viscous force and acceleration? Let me go back. So here, if you will see, your velocity diagram up to the entrance region is keep on changing. Here was different, here was different, here is different. But after that there is, if you will draw the here one, so there is no change. So here what will happen, if your velocity is changing, it means your acceleration, uh, this zone is having acceleration. So the meaning of this line is you can easily understand from here. The pressure is balanced, whatever the pressure difference in the pipe, because in we are talking about here the pressure flow, pressurized flow. So water will flow from pressure difference. So pressurized balance by here the viscous force as well as acceleration. But in case of fully developed, there is your pressure no acceleration, because of your velocity is not changing in the, if you will talk about this direction, let me draw your velocity diagram is not changing. If your velocity not changing, then there is no acceleration. So your viscous force is balanced by, or pressure is balanced by the viscous force. So now, so pressure and the shear stress, these two things is very very important. So the force balance, the pressure force is need to overcome the viscous force generated. And always remember, when we discuss about any topic or any analysis in the case of pipe flow, we always consider uh, in the fully developed region. Always remember, even assumption is not written, then you just, it is pre-assumed for every questions whatever we have discussed here, and what we will discuss here. So always remember, we discuss in the fully developed region, not in the entrance region. So even assumption is not written, it's self understanding, should be it's self understanding. So full we are discussing in the fully developed region. So here also, so that's why here written your force balance, that is your force is needed to overcome the viscous force. Because here why we are discussing about the viscous force and the pressure force, only two things, not acceleration, because we are talking about the your fully developed region. Also the energy balance, that is work done by the pressure force, is needed to overcome the viscous dissipation throughout the fluid. Okay, maybe some network. Okay, slide is visible, please.
Yes, sir. Visible,
Okay,
sir.
okay. So now we will not discuss much about this because sir is already told everything. So just we will go in the question, question and answer. So fully developed laminar flow, you already see whatever we will discuss. So Newton's second law, how will here it is very important. This one is very important slide. So always remember the fully developed laminar flow. You can calculate the equation of fully developed laminar flow in the pipe can be derived using the three approach. This is very important because for solving any problem we need to first origin, then after you can go one by one. So if you will know origin or the basic things, then you can easily correlate the thing and you remember for a long time. So it is very important. So equation for fully developed laminar flow in the pipe is using the your Newton's second law and also Navier-Stokes equation. Uh, I think up to 8 week we have not discussed about the Navier-Stokes equation, but maybe in the next class we'll discuss more about the Navier-Stokes equation, how to derive and all. And also one approach is the dimensional analysis is very common in fluid mechanics. So so this is basically your fluid element and all, sir has discussed earlier. So we'll not much discuss these things. So some basic mathematics, these are also important. So energy in the fully developed laminar flow. So here I want to tell something. Uh, if you will see here energy in the fully developed laminar flow. So one thing I have said earlier, like that whatever we will solve the equation and problems. So always remember the we are talking about in the fully developed region also itself. So consider the energy flow between the two locations. So if your pipe is like that and water is flowing in this direction due to the pressure. So if here point 1 and here point 2, so your Bernoulli's equation at point 1 and your Bernoulli's equation at point 2. So here just I want to show one thing. Here is a alpha term, that is your kinetic energy correction factor. So if the kinetic energy correction factor is why we have taken here, because uh, you know already this velocity is, that is the at every point your velocity is different. Here is the different, and here is your velocity different, here different, here different, everywhere your velocity is different. So considering the average things, that is the here at every point your velocity is different. So considering the single velocity value, so we have taken the kinetic energy correction factor or the energy correction factor. But as per the analysis for uniform velocity profile, for uniform velocity profile, like if your velocity profile like that uniform, that is the inviscid. If your water is inviscid means what? There is no friction between or no here is the velocity is that much, there is no slip, not consider the no slip condition, that is the uniform velocity. If velocity profile is uniform, then alpha is equal to 1. Another also, for fully developed flow, alpha is equal to 1 also. And what is L? You know already, it is the head loss or energy loss. So this is that much. So here one thing is very very important. If you will see this formula we will use in the problems also. Remember this formula we will use. Okay, and del P by del L sine theta. This formula you remember. Now the turbulent flow you know already. The flow is zigzag way. So sometimes we average, we find the for analysis of the turbulent flow, because we have not the develop at the mathematical tool to use the directly utilize or directly analyze the turbulent flow. So we divide this to the your flow velocity divide in the two things. One is the is instantaneous, that is the your time average velocity, and another is the fluctuation velocity. So we will discuss. Sir has discussed a lot. I will not discuss here. Some Prandtl mixing length theory. It was a very breakthrough discovery in the open chat in your the fluid mechanics. So if have you the more interest, please go through some standard book and all. So okay, that's fine. So first of all, we have one question regarding the your friction loss. So question is that find the Darcy's head loss. Find the Darcy's head loss due to the friction in pipe of diameter 300 mm and length 50 meters, through which water is flowing at a velocity 3 meter per second, and take the value of friction is 0. That is your friction factor here is given 0.01024. So please try to solve this question and give your answer in the comment box. So let me share. So the question is visible.
Yes, sir.
Yes, please try to solve the question. And here you think about in this question is given the friction factor, not the friction coefficient. So always remember the relation between the friction factor and the coefficient. Sometime someone might be confused in between these two things. So I will show you how it is related. Just please you take 2 minutes for solving. You can write in the comment box also. So still you are solving, please. Hello, am I audible? Hello, Ratnasri, am I audible?
Yes, sir. Audible, sir.
Okay, okay, let me discuss. So here is nothing big thing. So here the Darcy's head loss due to the friction in the pipe of diameter D. Your diameter is given 0.3 meter and your length is given 50 meter and velocity is given 3 meter per second and the friction factor is given 0.01024. So these all data is given and you need to find out your Darcy's head loss. So you know the formula for FL V square by 2ZD. So here the this that is your, if you will take the F dash, so your friction factor is equal to 4 times of friction coefficient. So here the friction coefficient is not given directly, the friction factor is given. So FL V square by 2ZD and put all the value, you will get the answer 0.01024 into L is 50 and your V square, if you will put, it will come out 9.81 and it is given zero point 0.3. And when you will calculate, let me calculate, 0.01024 into 50 into 9 divided by 2 into 9.81 into 0.3. So it will come around 7828. So this is the answer. Okay, 7828. Okay, now moving ahead. So here the ratio of your momentum correction factor to energy correction factor for a laminar flow in pipe. So here the condition is given laminar, not turbulent. You need to calculate what? Momentum correction factor to energy correction factor. That is beta by alpha. You need to calculate laminar in pipe flow. So previously I think I was okay. First please try to solve and then I will show the all values and all. And in between I want to write one question from the gate. Please try to solve this question. So slide is visible, please.
Yes, sir. Visible,
Okay,
sir.
okay, thank you. So please try to solve very quickly. Then I want to write one question is very, very important. So before discussing this question, let me first show some question regarding the equation. This is the question gate 1996. The equation gz plus v square by 2z plus p by rho is constant along a streamline. Hold along a streamline you know holds true for option A is given: steady, frictionless, compressible fluid. Frictionless, compressible. B option is given: steady, uniform, incompressible. C option is given: steady, frictionless, incompressible. And option D is given: unsteady, incompressible. So these four option is given. So you are telling the option D is correct for that. Okay, let me check. So here I think yes. Here I have given some values for laminar and turbulent. In case of laminar and turbulent pipe flow, so your alpha, that is your energy correction factor, kinetic energy correction factor, in case of laminar it is 2, and if water is flowing turbulent it is 1.33. And if your correction factor, that is your momentum correction factor beta, in case of laminar 1.33 and 1.2 in case of turbulent. So this is the table. So now first look the your answer question. The question is about, where is the question? Yes. Need to calculate the ratio of momentum correction factor, that is your momentum correction factor in case of laminar flow it will be 1.33, and in case of correct, that is your beta by alpha, and your alpha is 2 in case of laminar. So if when we will calculate 1.33 divided by 2, it will come 0.665. Yes, the option number C is correct for that. So please try to solve the question number whatever I have written here. Let me question number put it 1, or question number A. So what is the answer for this question? Based on this question I have one question, that is a numerical question. So please try to solve this, the written question. Okay, so answer of this question is basically this is the Bernoulli's equation here. So Bernoulli equation derived using the lots of assumptions. So assumption is like that your fluid should be ideal, that is inviscid fluid. There is no viscosity. That is non-viscous. Fluid should be ideal, fluid should be non-viscous, steady flow, continuous flow, and incompressible flow, irrotational and applicable through one streamline. A streamline. So lots of assumptions are there. So here we have put only the three combination of three. So for Bernoulli's equation, basically your steady, frictionless, and incompressible. Frictionless here nothing but the non-viscous. So option C is correct for that. But we have one question regarding that. The question is like that: a body is moving through still water. Water is still. Let us consider here one. I am showing the on here, that is still velocity of water here 0, and but whatever the body is moving in this fluid, the velocity of the body is 6 meters. If you will see in the channel, that is from this this graph showing the cross sectional view, if you will see from your top view, then what will look like? If this is the length of the your body, water body, so here is the, this is moving 6 meter per second. 1 meter ahead, your velocity of the fluid is, or the water is 4 meter per second. So the question is asking the pressure difference or difference in pressure between the nose and the point 1 meter ahead. So from, let's suppose point 1 and point 2, this is point 2, the pressure difference between point 1 and point 2, what is the pressure difference? So P1 minus P2. The question is asking like that. That's it. In the question is written, that's it. So in this question, there is not given any assumption kind of thing. Whether the flow is, that is your still flow, the fluid flow, that is your water flow is 0, velocity is 0, but due to the your movement of your body, or the velocity is 4 meter per second in the water at a 1 meter ahead. So here at undergraduate level, this is the gate, I think 1998. So at undergraduate level, we study generally, basically we assume we will apply only the, that is we already assume these things, the flow should be steady, frictionless, incompressible, this kind of thing. So throughout our the exam and everywhere, the all assumptions might be somewhere maybe the written, but in general case what I have seen, these type of assumptions are not written in the question because lots of assumption. So always remember, assumption is not there, but uh, you need or you can apply in the objective kind of thing question, you can apply the all assumptions, or you can pre-assume, or you maybe think this question is framed like the frame using the assume, this kind of the assumption whatever you have assumed in the Bernoulli's equation. So at undergraduate level, you always apply your Bernoulli's equation for pressure difference and maybe the for velocity calculation if assumption is not or maybe some if the question is not specified, though you apply this Navier-Stokes and other things, so you always try to apply these things in the question. So please try to calculate your answer for this question. So here you need to calculate the pressure difference. So how you will calculate this pressure difference? Please take time. So your V1 is given 6 meter per second, V2 is given 4 meter per second, and we have already assumed the things like that your fluid is steady, incompressible. Even the question is not given, but you should assume at your undergraduate level. Otherwise, in any question, the if examiner want to ask some different thing, then definitely uh, he will give some another hint about the question. So okay, V2 is this, and the length in between is given 1 meter. So please try to solve this pressure difference. So you can apply in this question the Bernoulli's equation, boys. Or you may assume your body or your point 1 that is on point 2 at the same level, that is ZU. Z is 0. So here the Bernoulli's equation is nothing but P1 by rho z plus V square by 2z plus Z1 is equal to P2 by rho z plus V2 square by 2z plus Z2. So here there is Z is 0, so you can assume 0 these things. But P1 minus P2 divided by rho z is equal to V2 minus V2 2z minus V1 by 2z. V2 square here. So if you will put the formulas, what will, here is the square. So V2 is 4 square, that is 16, by and 6 square, that is 36. So if you will minus these things, you will get 20 into, you can take the 1000 here as a density of water. So 10. So 10,000, here is the P1 minus P2. So it will come in the minus here. So your difference is nothing but your 10,000 Newton per meter square. There's a difference. So we approach like that. Now the question is very very important here. One question. The valve. Well, let me take 5 minute break. Okay, now we will see the question number. That is the another question. The valve in a piping system cause a 3.5 meter head loss in the piping system. If the velocity of the flow is 7 meter per second, the loss coefficient of this valve is, that is the option A 0.87, option B 1.69, option C 1.25, option D 1.4. So please try to solve this question. So the answer of this question is basically you know already the coefficient, that is the loss coefficient, is nothing but, if you will know, your head loss is equal to what, some coefficient into v square by 2z. So here asking about the coefficient, so head loss is given 3.5 and v square by 2z. This is nothing but into 2 into 9.81. So it will come around, let me calculate first, 3.5 divided by 49 into 2 into 9.81. So this will come around 1.40, 1.401. So option D is correct for that. Let me increase the size of the, okay. Oh, I think highlighter is fine. Okay. So now moving ahead on the another things. So solution is this. So if you will see here, it is like that. Now the question is the water. The question is here, the water flow in one point, that is the 15 centimeter diameter pipe of velocity 1.8 meter. If the head loss along the pipe is estimated to be 10 meter, the required pumping power, here asking about power, pumping power to overcome this head loss. So your G value is given already 9.81, you can consider, and your velocity is given 1.8 meter per second, and your diameter of the pipe is given, diameter of the pipe is given 15 centimeters, so you can write like that. So how you will calculate? Just please take 2 minutes or 3 minutes. If you will think from your previous knowledge, what is the power, that is force by work done by time, work done per unit time. So utilize this concept from fluid mechanics concepts, then you will easily calculate these things. And today I have also some, I think, let me finish first this question, then I will show you. So here the power value is nothing but, let me first give some little bit hint. Work by time you know already, that is force into displacement divided by time, and force into time is nothing but mg divided by time into d. So mg is nothing but your m dot, we have already discussed, mass flow rate, into your d is nothing but here the head loss. This is formula from the basic physics, but in case of the fluid mechanics, here the your displacement in terms of head loss, that is, if your head was up to that much, so your head is reducing in between, reducing from top to up to that much, that is the 10 meter. So here displacement is nothing but your head loss. You can write the HL. So m dot is what? Rho AV into G into L, that is HL. So rho is nothing but 1000, because I think is water is flowing here. Here's that's it. Rho A is area, pi by 4 into d square, 0.15 square into 9.81 into 10. Just please calculate these things. Let me first calculate, then just I will 1000 into pi by 4, pi by 4 into 0.15 square into 9.81. 1000 into pi by 4 into d square 0.15 square into 9.81 into 10. So it will come 17. Here I have here is the density, here is your area, and velocity term is here. So let me put it here. Your velocity is 1.5 meter per second. 1.5. So here is the answer. So whether the calculation mistake sum pi by 4 into d square into 1.8 into 9.81 into 10. So it will come 31 this much, and in that is what, and if in kilowatt divided by 1000, so it will come. So here your velocity is 1.8, not 5. So 1.8. So here 3.12, 3.12 kilowatt. Okay, that's it. Now, yes, so just I want to show you some, because I was going through some previous year questions, that is the Bihar Public Service Commission. So from the fluid mechanics, the level of the fluid mechanics question, just to see, let me show you first. This is important also, whether you are studying. Yes. So first is the mathematics, then it is, yeah. So here, what is actually the question is, if you will see, the question is not big, having the big challenging. So the concept of continuum in the fluid flow assume that the characteristics length of the flow is smaller than the mean free path of the molecule, larger than the mean free path of the molecule, larger than the dimension of the suspended particle. So this type of question we have already discussed in the at introductory. I think in the first and second lecture I have discussed about this question. Second question is what? In a fluid flow, point A is at higher elevation than point B. The head loss between the point is HL. The total head at A and B are HA and HB respectively, the flow will be take place. So this is a simply application of the Bernoulli's equation. So it's nothing but at point 1 and point 2 is here, point A and point B, and the higher elevation, the point A is at higher elevation. So here is your point A, here is point B because it is higher elevation. The head loss between the point A and point B is HL. Okay, and the total head, that is total head, is nothing but P by rho z plus V square by 2z plus Z. It is equal to, if at point 1 is HA, at point B is HB. So HB equal to HA plus HL. The flow will be take place from A to B or B to A. So always remember, flow from higher elevation, not higher elevation, higher energy to lower energy. Higher energy to lower energy. So higher energy on which side? At side B. B is having the higher energy. If you will here put, let first assume that if it is, because it here is the addition, and if you will calculate HA, your HB minus HL. So if you will see these two equations, so here HA will be, your HB will be more than HA. So water will flow from which side? From B to A. So this type of question you can think. A laminar boundary layer has the velocity distribution given by this and this. The displacement thickness is what? So this is very displacement thickness is nothing but, you know already, 1 minus u by del u d delta. So you can calculate the mean drag coefficient. These things we have already covered. So this type of question is coming. So you can easily calculate and you can easily able to give the answer of this question. So now coming on the our discussion. So here is very important question, similar the previous one question. So a water, so here the water, that is your gamma W is given 9.879. Flow rate is Q is equal to 0.3 meter cube per second through a pipe AB. One pipe is given, AB pipe, length is 10 meter. The uniform cross section, that is area and area both side at both, that is throughout the cross section is similar. Okay, the end B above end A. Oh, similar question, the previous one. But in the previous question, what was A was at the above. So here B is above. Okay. And theta is there. How much theta? 30 degree. The For the pressure 12 at B, corresponding pressure at A. PA need to calculate. PB is given. And this length is given here 10 meter. So please try to calculate. PA how much? So here you can also apply the Bernoulli's equation. This is very at undergraduate level. Bernoulli's equation you may expect one question in each examination related to civil engineering, whether it may be some on question on assumption or maybe on this type of problem. So you can get you can expect the question from this topic. So if you will ask some layman, then what will here happen? Who have not the knowledge of the pressure and all the head. So one can say easily water will flow from B to A because it's a higher elevation, but not like that. After calculation, just we will see whether the pressure at point A is more and pressure at point B is more. So if the pressure at B is more than A, then flow from B to A. Otherwise, if the pressure at A will be more than B, then your water will flow from A to B. So let me write the Bernoulli's equation. So before applying the Bernoulli equation, just for you always remind in your mind the assumption behind the Bernoulli's equation. So in the practical, you can sometimes it is very difficult to apply your Bernoulli's equation at the practical level. But at undergraduate level, so this is just initial stage of learning the fluid mechanics. So now we apply the your pressure things at A. Red one. So PA divided by rho z plus V1 square by 2g plus z. ZA, if you will write here, A is will be fine. Similarly for B, PB by rho z and something like that. But here your VA and VB will be same because your cross section area is same. Discharge definitely area into velocity. If your cross section area is same, then your VA is equal to VB. So these two terms will be neglected from here. So here for just your plus ZB. Here I think head loss is not there because of the smooth pipe. Here is not given, but you may consider here the This is the smooth pipe. Smooth pipe, so head loss is not there. So what about this length? This length is nothing but it will be, here is the theta is this, so this component will come around your, simply if you will apply the triangular rule, so this will the your 10 sine theta sine 30, so this is 5. So your PA is given, PA you need to calculate, ZA is 0, so what is remaining? PB, PB is given 12, rho z, rho z is nothing but gamma W, so it is given, PB is given kilonewton per meter square, your gamma W is also given in kilonewton per meter square, so this is fine. Now plus your Z is 5 into PB and Z value I have put it, and VB is 0, and here you need to multiply with this rho z value, that is 9.879. So you will get, let me calculate, 12 divided by 9.879 into, that is plus 5 into 9.879. So this is 61.39, or you can say 61.4. So this is in kilonewton per meter square. And here, for your sake of just I want to take some analysis. So here your PA is greater than PB. So your water will flow from this direction to this direction. So always remember, if your point is at the level of B, that is a higher level, so it not necessary to water will flow from higher elevation to lower elevation. In pressurized flow, your water is flow from higher pressure to lower pressure, or higher energy to lower energy. But in open channel flow, you can say one term is your water will flow from higher level to a lower level. But in pressurized flow, you cannot say these things. Okay, so I think someone joined. Not. So now moving ahead on another question. That is, the first question is very very important, coming from the Prandtl mixing length theory. So this is also important, and hint of this question I have given. Please go through the all points, then try to give the answer of this question, because this is very new question, or very important question at the level of under as well. The Prandtl mixing length in pipe flow is constant. That is the what is mixing length and all in this point is everything is given. So please first try to read all the points, then try to give the answer of this question. And the zero at the point, zero at the pipe wall, and a function of the shear stress at the wall, and the function of Reynolds number. So basically, how when the top this your Prandtl mixing length theory come in picture for analyzing the turbulent flow, basically not in the lame, but we face the difficult, or the research scholar and scientists face the difficult
for analyzing the turbulent flow, the Prandtl gives a very informative thing in terms of Prandtl mixing length theory for analyzing the turbulent flow. So please read all the 5 points, then try to give the answer of this question. Which one will be the correct? So whether anybody join or not, okay. So the point is what? Point one is telling about the Prandtl mixing length is zero at the pipe wall as the flow is laminar. That is negligible velocity fluctuation at the boundary of the pipe wall. So we have discussed earlier also. Let me put it in full view mode. So we have earlier also discussed about these things. In the laminar flow, there is no fluctuation. So mixing length will be zero, definitely. What is actually mixing length? In the second point is given, very decorately written. The Prandtl mixing length is the distance between two layers in the transverse direction such that the lump of fluid particle from one layer could be reach the another layer, and the particles are mixed in such a way that the momentum of the particle in the direction is conserved. That is, there is no loss of momentum. So what is actually the meaning of this? If your water is flowing, in case of turbulent, you know already the zigzag type of motion. So your water is flowing in the layer wise. So if we see at a very micro level, your fluid particle is like that. But in case of turbulent, your fluid particle from this layer to maybe jump at this layer, maybe at jump below level also, this fluid particle. So this is the length. That is the Prandtl mixing length is the distance between two layers. If it is one layer is flowing here, this is the another layer. If the water flow is turbulent, then this may be the from this layer your fluid particle may jump into this layer. Back. So what will happen here? So nothing. The distance, whatever the fluid is traveled from uh, one layer to another layer. So this is your the length, that is the Prandtl mixing length LM. But the condition behind it, this is the condition what is given, the particle are mixed in such a way that the momentum of the particle in the direction, that is in this direction, if your particle is uh, going in upward direction, so in this direction your momentum will be conserved. What will the momentum here? Momentum you know already, the your mass and velocity. So this should be the conserve. Now coming on the third point, the Prandtl mixing length is a model, that it is a mathematical model used to estimate the eddy viscosity. in the turbulent flow. Basically, in the turbulent flow, your shear stress in laminar flow is generally the write the shear stress in term of this. But in the turbulent flow, we need to write the eddy viscosity du by dy. So for calculating these things, we use the Prandtl mixing length model. We use another model also, but here we are discussing about the Prandtl mixing length. So eddy viscosity is a measure of resistance to the flow caused by the turbulent eddies in the fluid. So eddy viscosity what measure? It measure the resistance to flow. That is the if your water is flowing with, let's suppose, the 2.5 meter per second, so it eddy may try to resist your flow or reduce the velocity by the why, because of the turbulent eddies. So the mixing length, basically Prandtl try to model, give the mathematical model to solve this problem by assuming the eddies formation, that is the in turbulent flow eddies will form. Definitely in the turbulent flow eddies will form. That is a when you will go for some assumption of anything, then assumption should be based on the practical, not like that you have assumed which is not practical. So definitely you have seen in the various applications, some researchers assume like that the assumption like which should not in the practical, which should not applicable in the practical. So that assumption may be the limitation of that model or that mathematical equations. So like that we move ahead. The mixing length model assume that eddy viscosity is proportional to the distance between the fluid particle and nearest solid surface, known as mixing length. So what is it is basically the mixing length model assume that eddy viscosity is proportional to eddy viscosity is proportional to the distance between fluid particle, that is your, let's suppose, Lm, distance between fluid particle and the nearest solid surface, known as the mixing length. However, this length is not constant. This length is not constant. Why? Because it depends on the shear stress. Definitely it will be. And which is the force per unit area acting on the fluid at a pipe wall. Therefore, Prandtl mix length is not independent to the shear stress. So it is not independent to the shear stress. It will be depend on the shear stress. That is whether which type of your fluid is flowing. Definitely. The value of your Prandtl mixing length is not universal constant because of depend on lots of things. One of the your flow conditions also for all type of turbulent flow. Maybe your Reynolds number if greater than like 5,000, it is also turbulent flow. Reynolds number is 50,000, also turbulent flow. So all type of turbulent flow are not possible the your constant because it's depend on the how your eddies will form in the fluid. So it depend on the specific characteristics of the flow such as Reynolds number, which is dimensionless quantity that describe the ratio of inertia force and the viscous force in the fluid. The Prandtl mixing length also varies with type of fluid and geometry of the flow. Definitely, because based on the geometry, your fluid layer, that is the your mixing length, that is your distance between these two layer, will be depend on the geometry also and the fluid also, because your maybe if your fluid is very viscous, so what will happen, your even the very Reynolds number is very very high, then your might be chance your fluid will flow slight bit like this. If your density, if your viscosity is less, so at same Reynolds number, it might be fluid flow like that. So it's depend on your fluid type also. The Prandtl mixing length is not independent of the radial distance from the pipe axis because the shear stress on the other flow characteristics vary from distance. You know already your shear stress will vary with the distance in the pipe like that. If it is pipe, your shear stress is very like that. This question once in gate examination is asked, already asked. So the mixing length is generally larger at the pipe wall than at a, okay, where it is given. Okay, so the Prandtl mixing length is not independent of the radial distance from the pipe axis because of the shear stress and other flow characteristics vary with the distance from the center of the pipe. So mixing length is generally larger at the pipe wall. This is very important. This point is very important. You can expect this question in your exam or gate exam also and another exam. The mixing length is generally larger at pipe wall. That is if it is pipe. So here it near the pipe wall it will be. Than at the center of the pipe due to the higher shear stress at the wall. So this is the whole idea. So here you can give the answer for this question easily. So what should be the answer? The Prandtl mixing length in the pipe flow is constant, not zero at the pipe wall. If the flow is laminar, then here is not given. So we assume this is talking about the turbulent flow because the Prandtl mixing length come in the picture for analyzing the turbulent flow. So this will be neglected if so. A function of shear stress at the wall, definitely a function of Reynolds number, or not. We can here we can choose the very appropriate things kind. So here is the function of shear stress at the wall. This is the correct answer for here. This is also, so this one is correct for them. So now moving ahead, this is very very important question also. So I will discuss about some Moody's diagram, then I will finish the things. Or maybe I will record it. I will record the video of the next coming week because of some maintenance work is going on, or maybe I will maybe out of station during the holy period. So I will record the video and I will upload in the, that is the Excel sheet or on the YouTube. So please, for the coming week, that is the ninth week, maybe I'm not sure, maybe I can take online also, but 70% maybe I will record and upload before that is the before Tuesday, coming Tuesday. So okay, now we solve the question number 2. In a fully rough turbulent pipe flow, that is the fully rough turbulent pipe flow, the friction factor is a function of Re and that is your epsilon s, and D a function of epsilon by D, and a function of Reynolds number only, independent of both. So please try to keep the answer. Here we are talking about rough turbulent flow, not the laminar flow. Rough turbulent pipe flow. So you might be heard about the Moody's diagram for pipe. Here E by D, Reynolds number, here is the friction factor. So Moody's diagram come in the picture for calculating the friction factor in case of turbulent flow. So okay, let me show the figure. So here in the figure, if you will see, for laminar flow, your friction factor is nothing but 64 by I for laminar flow. So in laminar flow, only friction factor is depend on RE. If this question was about the your laminar flow, then you can go through the option, maybe C option. Yes, C option. If the flow was, but here the question is a rough turbulent pipe flow. So in the rough turbulent pipe flow, in the rough region, that is the your complete turbulent. This is actually from this, from here to here, all the your turbulent flow. But after this line, that is your dotted line, every here, this line, these all reason for the rough turbulent flow. So here you can see, if your Reynolds number is this, something something power n, and Reynolds number is this, something power n, here n1 and n2. So your, that is the your friction factor, almost friction factor is same. So in the rough region, if you will see, your, that is the no effect of the Reynolds number, whatever the Reynolds number is, that much or this much, your friction factor is depend on what, the pipe roughness. Maybe the pipe roughness is this, so you will see in this line. Maybe the pipe roughness is this, you will see in this line. Maybe the pipe roughness is this, you will see in this line. So but in this region, as changing your Reynolds number, what will happen here? This is the Reynolds number changing here, here is the another Reynolds number, but here also your E by, that is your E by D is changing also at both point, and also your friction factor also changing because it is a curve, but here is a very straight line. So in the fully rough region, your depend, that is your friction factor is depend only on what, a function of E by D. So option D is correct for that, and depend on both in this region, in this region. So smooth turbulent, or you can say the intermittent turbulent. So we have another question like that. So you can solve this question also. So the head loss of in 100-meter diameter one, and friction factor is this carrying the boundary shear stress in the cable. So here talking about the boundary shear stress. In this question, talking about a turbulent flow through a pipe, center line velocity is, that is a turbulent flow, you remember, not your velocity diagram very parabolic. Your velocity diagram like that. So center line velocity is given how much? 3.61 meter. Friction factor is also given 0.2. The mean velocity, what will be the average velocity, what will be the value? So please, this type of question you can expect in your exam. Or final exam of NPTEL, and also in assignment, definitely. So the formula is there for this question is 5.75 log 10 y by r into 3.75. So when you will calculate, your u value is given 3.61, and how you will calculate u star, you know already. This will be calculated by f by 8. Here is u is given, that is your shear velocity. So using this, if you will calculate, your answer will come around 3 meter per second. And how you will calculate this, your shear stress? So formula is HL is equal to 4 wall shear stress by rho z L by d. Everything is given here. Head loss is given, diameter is given, length is given, and rho z you know already. If it is water flowing, then 1000 is rho. So you can calculate this also. So with this, we'll conclude today. So maybe in the next week I will record the video and I will upload before Tuesday, and you can mail me regarding the whatever I will upload, any queries if you will have. So OP Moria gmail.com. So you can mail me on this whatever you have doubt, or in the previous class also. So thank you for today. So with that, let me stop the